Okay. Well, hello everyone. Welcome to the International Methods Colloquium. My name is Justin Essery. I'm an associate professor of politics and international affairs at Wake Forest University. This is my cat Bullet, who picked this moment to sit on my lap. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and also by Springer Publishing. This week, we have a speaker, Jesse Shapiro from the Department of Economics at Brown University and also the NBER, presenting a talk entitled Bounds on a Slope from Size Restrictions on Economic Shocks. Jesse's talk will last about 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. You can ask questions at any time during the talk, but questions will be held to the end of the presentation. If you wish to be recognized and ask your question via audio, assuming you have a microphone on your computer, please indicate this in the Q&A text box. Otherwise, I will read your question from the text box during the Q&A period. A link to Jesse's paper and also his slideshow will be available in the Zoom webinar chat window so that you can refer to it throughout the presentation. I will post those links right after this introduction. Now I'd like to welcome Jesse to the IMC. Jesse, welcome.
Thank you so much, Justin. I really appreciate the invitation and the chance to talk to you all about this work in progress. I want to apologize that I don't have a cat, so I feel like I'm missing something today, but hopefully that's okay with you all. This is work in progress with Marco Stenborg-Pedersen, who is a PhD student here at Brown, and also with David Same, who is a professor at Stockholm. And in this project, we're trying to approach what is a canonical problem in empirical economics, and I think also arises in other social sciences, which is to learn the slope of some outcome, say quantity demanded, with respect to some input, say price, in the presence of some unobserved factor, say preferences, whose changes over time might be related to the input. And we're going to imagine that we have time series data, so a finite series of observations on inputs and outputs, where the input changes at least once sometime during this series. And of course, we know that it's a canonical problem, that if we don't observe these shocks epsilon, then we cannot know the true slope theta of the relationship, which is what we're interested in knowing. For example, we can imagine, just to fix ideas, that we have a two-period data set. So here, following the convention in economics, I put price on the y-axis and quantity on the x-axis. And we can imagine that we have one data point here and one data point here. And it might be that the slope of the underlying relationship connects these 2 points. And so that would be represented by this, what we're calling theta double prime. But it might also be that preferences shifted between these 2 periods. For example, if preferences shifted positively, then the slope might be something more like this theta prime. Or if preferences shifted negatively, so what we would say is demand shifted inward, then the slope might look something more like this theta triple prime. And so we can't necessarily know from the data alone what is the value of the slope. But what you can observe from this construction is that given the data, any slope theta that we pick implies some value of the shock. And that's what's represented here. So here we've defined the shock delta epsilon 2 between the 2 periods to be the change in the output minus the slope times the change in the input. So this, according to our first equation, has to be the change in the shock. And here I'm using big delta to be the first difference operator. So given the data, any value of the slope that we pick implies some value for the shock. And there might be situations in which we're prepared on a priori grounds to rule out very large shocks. So for example, in the world market for grain, the main influences on demand are population and income, and the income elasticity is thought for a variety of reasons to be fairly low. So it might be reasonable to suppose that demand changes by no more than a few percent per year in per capita terms. We can formalize that kind of restriction by imagining that we are prepared to say that the shock cannot be bigger than some upper bound B. Imposing that kind of bound on the shock, like we do here, then implies a bound on the slope theta that we can represent graphically in our 2-period example like this. So now I've reversed the axes, I rotated them, I put quantity on the y-axis and price on the x-axis, and I'm also now representing things in first differences. So this is now the change in quantity between these 2 periods, and this is the change in price. And any demand curve that we specify here, any slope theta, implies a line through the origin. So for example, the one we were calling theta double prime before that connects the 2 points, that's a line through the origin that runs through this point here. Well, if we can put a bound on the size of the shock, that is to say that it's no bigger than some amount b, then that gives us an interval around the observed data, and we know that any demand curve or any slope consistent with that bound has to pass through these points, has to pass through this interval that we've drawn around this point. So that means that if we're prepared to impose a bound on the size of the shock, then we've also imposed some maybe useful bounds on the value of the slope. Here, I'm showing you this only for a 2-period data set. We're going to be interested in more general situations. And in fact, it's possible to generalize this idea to t periods. And that's one of the things we're going to do in this paper. So what I'll do today is show you how we can characterize the bounds on a slope theta from bounds b on a generalized mean of the absolute value of the series of shocks, delta epsilon. Along the way, I'll also have something to say about which bounds are consistent with the data in the first place. And then after completing the characterization, I'll show you how we can apply this to the world market for grain. And I'll argue that bounds we might have been prepared to impose ex ante are actually potentially very informative for the parameters that we are interested in that setting. And if there's time at the end, I'll try to spend a few minutes extending our analysis to show what happens if we want to allow for a nonlinear or non-separable relationship between the input and the output. Okay, so let me now take you through the characterization we're able to provide for the general case of t time periods. To do that, we need to establish some definitions. So first, for any d-dimensional, any vector v that has dimension d, and any scalar k that's greater than 1, I'm going to define, and this is a standard definition, the generalized k-mean, which I'll write as m sub k of v, to be this expression here. Okay, this is probably a familiar expression to many people. In the limit where k is equal to 1, this is just an arithmetic mean. In the opposite limit where we take k to infinity, this is just the maximum element of the vector. And if we want to pick an intermediate familiar case when k equals 2, this is the root mean squared value of the elements of the vector. Having defined this generalized k-mean, we can then take, for any slope theta, we can take the sequence of shocks implied by that theta, that's this definition here, we can turn that into a vector, that's this thing here. We can take the absolute value of that vector, and we can compute its generalized k-mean, and that gives us this object here, which we're going to call m hat of theta for short. So that's the generalized k-mean of the sequence of shocks implied by the data and a particular value theta of the slope. With those definitions in hand, we can state the problem that we're interested in as finding the set of values theta such that the generalized k-mean of the shocks implied by that theta is no larger than b. And that set is what we're going to call big theta hat. That's this thing here. It's going to depend, of course, on b. And that's what we're going to be interested in knowing about, just like in the 2-period example. So we're going to be interested in learning about this set big theta hat b. And again, going back to the 2-period example, just to make this concrete, in this example, this is just the set of slopes that fall in this green region here. So it's the set of slopes that pass through this interval that we've defined by taking the data and moving up or down by b. In this 2-period example, then, it's very straightforward to define this set of feasible slopes theta, but it's also possible to do it for a general number of time periods t. To do that, we make the following observation. This function m hat of theta is strictly decreasing up to some minimum, and then strictly increasing after that. And that means that it has a shape kind of like this. So it declines up to some point here where it reaches a global minimum, and then it increases everywhere thereafter. Well, that geometry is very helpful for characterizing what we want, because what we want to know is if we put an upper bound on this generalized k-mean, what does that tell us about the possible values of the slope theta? Well, let's put an upper bound on it. For example, let's say that we know that the generalized k-mean can't be more than this amount b. Well, that means that the slope has to fall between this point here and this point here, because those points define the interval in which m hat of theta falls below this given bound. I have a prettier looking version of that same construction on this slide. So what we can say now is that given this bound, we can define an interval where the endpoints of the interval are here called theta lower bar and theta upper bar. And we know that if the generalized k-mean of the shocks has to satisfy this bound, then the slope has to fall inside this interval. Here's that same statement just stated in math. For any attainable bound b, we know that the set of slopes consistent with that bound is given by an interval where the endpoints of the interval are the solutions to a nonlinear equation that sets the generalized k-mean of the shocks equal to b. Now, if you're paying close attention, you notice there's the word attainable, and that is there because it can happen that some bounds b are inconsistent with any slope theta. That is, they can be refuted based on the data alone and the model, even if we don't have any a priori information about the slope theta. So let me briefly digress to explain that because it's going to show up in our application. So going back to the plot we had before, this is the global minimum value of the generalized k-mean of the shocks. If that value is above 0, then that means that there's a range of bounds b that we simply can't impose. What that means is that we know, even if we don't know anything about the value theta, we know from the data alone and the structure of the model that the minimum k-mean of the shocks has to be at least this amount here. Okay, and we're going to call that amount b lower bar because it's going to tell us the lowest possible bound we can hope to impose on the shocks. This has a constructive implication independent of what we want to say about the implications for theta, because it means that we can say something about the minimum magnitude of the shocks necessary to rationalize the data, even if we don't come in knowing anything about the slope theta. So we can learn something from the data about the underlying shocks in the system, even if we don't know the slope and we're not prepared to make any further assumptions other than what we've already written down. Okay, so that's a bit of a digression. We'll come back to that in the context of the application. Coming back to our main story, in general, so we want to be able to apply our approach. So that means we need to be able to calculate these endpoints. And in general, they're pretty easy to calculate because, as we saw before, the endpoints we're interested in are just the solution to a nonlinear equation that sets the generalized k-mean equal to b, and it's a well-behaved nonlinear equation in one dimension. So it's pretty easy to solve it numerically. And in some cases, we even get analytic characterizations. For example, in the case of k equals 2, that nonlinear equation is a quadratic equation. And of course, we know how to solve that. So we get endpoints that look like this. They're centered around this value here, which is this ratio of what we're calling s hat qp to s hat pp. That's defined over here, in case you want to follow that. What's important to say about that is that this value here is the value that minimizes the implied mean squared shock in the model. And that value is also the slope of a least squares regression of delta q on delta p, where we include no intercept. That's intuitive because this is basically telling us what is the line through the origin that has the best least squares fit to our data. And that is the slope that's going to minimize the implied mean squared shock, which makes sense because that's how we construct the least squares estimate. So we get an interval that's centered around a least squares estimate and gives us a range plus or minus that estimate, where the range depends on this bound b. Another case that turns out to be very tractable is the case of k equals to infinity, where now we're bounding the maximum possible shock, taking the maximum absolute value of the change in epsilon. And in this case, again, the set of interest is an interval. And again, it has a closed form characterization, arguably a little less pretty than the one before, but actually it's going to turn out that we'll use this case quite a bit in our applications because it has a very intuitive geometric structure in practical situations. Okay, so that takes us through the characterization of the sets we're interested in the general case. Now let me walk you through an application to real data that hopefully will make clearer why, how this works and why we think it can be useful in social science. Our setting is going to be the world market for food grains, and we're going to follow an existing paper by Roberts and Schlenker in 2013. This paper used annual world data from 1960 through 2007 to estimate the elasticity of demand and elasticity of supply of staple grains at the world level. The authors assume a log linear model, and they achieve point identification of the parameters of interest via exclusion restrictions. For now, we're going to maintain linearity in logs, so we're going to inherit this assumption from them, but we're not going to impose any exclusion restrictions. And instead, we're going to see how far we can get by imposing limits on the size of the shocks. In the talk, I'm going to focus mainly on the demand equation. If you're interested in looking at the supply side, we have analogous plots for those in the paper that Justin's linked to. And I'll come back and talk very briefly about the supply side towards the end of the application. Mostly I'll focus on demand because that's sufficient to get across the main ideas. For demand, the price is going to be the log of the average current month future price of grains delivered in the present year, measured in 2010 US dollars per calorie. And the quantity is going to be the log quantity of grains consumed at the world level, measured in calories per capita. The last ingredient, so this is one ingredient we need to apply our approach. We need some data, but the other ingredient we need is we need bound speed on the plausible size of the shocks. And in this application, it's possible to say something about that because this is a very widely studied market. A lot of evidence indicates that the major determinants of demand for grain at the world level are world population and world income. We're doing everything here in per capita terms, so we've scaled out population, and that leaves income as a major determinant of the unobserved, potentially unobserved shocks, epsilon. A lot is known about the elasticity of demand, the income elasticity of demand for food. This is one of the most widely studied empirical quantities in the history of economics, going back to Engels' work and many others in the 19th century. So it's something about which much has been written. And a paper a few years ago by Vallon et al., which is mostly focused on forecasting the future demand for food, helpfully summarizes a lot of different quantitative models that people have put together to try to characterize world food demand. And those models imply a range of income elasticities from 0.09 all the way up to 0.37. These income elasticities are in turn informed from a variety of different kinds of data, including microeconometric analysis and cross-country analysis. To be conservative, we're going to focus on the upper end of this bound. So imagine that the elasticity of world demand for food is 0.37. Well, we know how world GDP per capita has evolved over the study period. That's easy enough to measure. And so we can ask, if the true income elasticity is 0.37, what kinds of shocks does that imply to world food demand? And the answer is that if you take that value of 0.37, what you conclude is that the largest income-driven shock to demand over this period was about 0.05. That's this number here. The largest, the root mean squared income-driven shock to demand over this period is about 0.02. And so in our analysis, we're going to consider bounds up to about twice this size so that we can be leaving some room for shocks that are driven by changes to things other than income. So we're already taking a pretty conservative approach by taking what is a reasonably high income elasticity, and then we're going to go even further than that to take a look at a wide range of plausible bounds. Okay, so let's take a look at what this approach delivers in this application. So here's the data. This is just like the plot I showed you at the beginning from the 2-period example, only now it's from a real data set. So there are more periods, and it's a little less stylized, but same idea. On the x-axis, we have the change in price. On the y-axis, we have the change in quantity. And now what we can do is we can draw an interval around each of these points that has a width given by our bound B. And just like in the 2-period example, what happens if we do that is that we know that the feasible slopes all have to imply demand curves that pass through these intervals. So to draw that a little more nicely, let's pick a value of 0.07. So this is about 40% bigger than the biggest shock from income alone. And so if we say that the shock to demand is no bigger than 7% per year, again, no bigger than 40% more than the largest income-driven shock to demand over this period, then we know that the demand curve has to pass through all of these intervals that we've drawn here. And of course, because usually we assume that the demand curve has to slope down, we also know that it has to pass through this quadrant and this quadrant. So that gives us the following picture. This shaded region here in gray now tells us the set of demand curves that are consistent with the model and with the restriction that demand shifts by no more than 7% at a given price between any two adjacent periods. We can then ask what slopes are consistent with this bound. And of course, the answer is going to be all slopes that imply curves that pass through the shaded region. And we can do the same thing for any bound B. So here we just picked an example, 0.07. It seems like a kind of reasonable example, but we can look at others. And so what we're doing in this plot is depicting the implications of a wide range of bounds. So to explain the axes here, first look at the x-axis. This is telling us the bound on the shock to demand that we're imposing. And the axis is broken over here. And the reason is that has to do with what we said before about attainable bounds. So the data imply that there must have been at least one period with a shock at least this big. Any bound below this point here is infeasible. We actually can rule it out. So even before we get to talking about the slope theta, we've learned something, I think, from this analysis, which is that there must have been a period with a 3.5-ish% change in demand. And that's not unreasonable given what we saw from our analysis of the income-driven shocks to demand that we did earlier. Looking at 0.07, which is a bound that we argued before was kind of reasonable and maybe even a little bit conservative. This is unfortunately not very vertical line, but hopefully gets the point across. What we can say here is that the elasticity of demand is no bigger in absolute value than 0.12. So that is already, I think, in some sense, a pretty informative statement because it says that the price elasticity of demand here is pretty low, that the demand for food is pretty price inelastic. And it's also informative in the sense that it zooms in pretty close to the confidence interval obtained by Robertson Schlenker in their analysis. So here, this horizontal line is Robertson Schlenker's point estimate, and the shaded region is their confidence interval. And so by imposing what I think is a priori plausible bound on the size of shocks to world food demand, we have been able to conclude that the slope can't be much bigger than 0.12 in absolute magnitude. And that already gets us pretty close to the conclusion of the Robertson Schlenker study, a big takeaway of which was that world food demand was pretty price inelastic. So this analysis establishes a sense in which we think this bound is informative. And of course, if you don't like that bound, you can look at the implications of other bounds, and they're all depicted here, where we're just showing through this line here the upper and lower bounds implied by our analysis on the slope of the demand curve. This is all for the case of k equals to infinity when we're bounding the maximum possible shock, but we can do exactly the same kind of analysis for any k. So just to illustrate, here we're bounding the root mean squared shock. Of course, the plausible bounds are different because we're bounding a different thing. And this, again, is informed by this analysis of income shocks that I showed you earlier, but the conclusions are pretty similar. And in the paper, we show the same kind of analysis for a whole range of geometries, so basically a whole range of values of k. So taking what we've seen so far all together, what I think we have found is that imposing a priori reasonable bounds on these shocks delivers informative bounds on the slope parameter that we're interested in. And along the way, we can also say something about what the shocks must have been just from the data alone. So that's an aside. We can also use the same approach to impose bounds on functions of parameters of interest. So to illustrate that, Roberts and Schlenker in their paper are very interested in this quantity here. It's the inverse of the sum of the absolute value of the demand elasticity and the supply elasticity. This is of interest because it tells you if you take a certain amount of quantity off the market, how much that's going to cause prices to increase. And Roberts and Schlenker are interested in that in part because they're interested in evaluating the effect of the US renewable fuel standard on equilibrium food prices. From their analysis, Roberts and Schlenker conclude that the estimated multiplier is economically substantial, so that this thing gamma here is a reasonably large number, and they conclude that because both the demand and supply elasticities that they estimate are pretty small. And they argue that that's interesting in part because it means that US ethanol mandates may be having a large effect on world food prices. We can try to impose bounds on this same function of these parameters here by just asking for if we impose bounds on the size of the demand shocks like we've already done, and we similarly impose bounds on the plausible size of the supply shocks, and then we take the set of demand elasticities that are compatible with our bounds and the set of supply elasticities that are compatible with our bounds and pass them through this function gamma, then we can ask what is the set big gamma hat of possible values of this multiplier. I've already shown you our analysis of this set big theta hat for demand. In the paper, we have a corresponding analysis of this set big theta hat for supply. And if we put them together, we get this picture here, where we can see that actually our approach is again informative in the following sense. So this light gray plane here, this is Roberts and Schlenker's estimate, and a big conclusion that they reach is that this is a reasonably big number, so that taking a few percent of quantity offline has a potentially large effect on equilibrium prices. And what we can see here from looking at this vertical axis is that by imposing reasonable bounds on supply and reasonable bounds on demand, we can conclude that this multiplier must be reasonably large, even without imposing any exclusion restrictions. So this illustrates a sense in which this approach can also be informative for functions of parameters of interest, and in this case, allows us to reach a very similar conclusion to the authors in their original study, but via a quite different route, using other information about the unobserved shocks. Everything I've shown you so far assumes that the underlying relationship between price and quantity is linear. And in our application, the authors make that assumption. So we can think of this as inheriting that, this analysis as inheriting that linearity assumption from the original application. But it's nevertheless interesting to know what would happen if we relaxed it. And so let me spend, I think I have a few minutes, so let me spend a few minutes speaking to that. Suppose that there's some unknown function Q such that the output is equal to Q of the input plus the unobserved factor. So now we've replaced our slope with an unknown function instead of just an unknown parameter. And I'll note here that we're writing this model as separable. So we're still assuming that the epsilon lives outside of this function Q. But in the paper, we show how a very similar analysis can be done, even if we allow for a non-separable relationship. Given this relationship here with an unknown function, we can rewrite the change in quantity as an average slope here times the change in price plus the change in the unobserved factor or the shock. So this average slope here is given by the value of this function Q at the price at time t minus the value of that same function at the price at the previous price divided by the change in price. So it is truly the average slope of the function Q over the region from pt minus 1 to pt. So we can rewrite the change in quantity in this way. And what that means is that we can, because this has a linear structure, it means that we can use a very similar approach to the one I showed you before to impose a bound on the average slope between these two time periods. And that's what we're doing here. So this set here tells us the bound that we can impose on the average slope between period t minus 1 and period t. We've gone ahead and calculated that in the context of the Roberts and Schlenker data, again, using this bound of 0.07 that we saw before, which remember is about 1.5 times the largest income-driven shock to demand over this period. And just to explain this plot, what you're seeing here is for each year, the set of possible average slopes between that year and the preceding year. These sets now, unlike before where we got a single bound that was uniform over the whole time period, here these sets or these bounds are different for different time periods because we're bounding the average slope, and since this function is nonlinear, its slope can be different at different points. And there are definitely periods in which this approach is not very informative. So like right here, the bound exceeds -1, so that means that we can't even exclude that demand is price elastic. But in most periods, we can. So in most periods, we can conclude that demand had to be inelastic between that period and the preceding period. So to put that another way, knowing only that the shock between two periods cannot have been more than 0.07, we know that in most periods, demand had to be inelastic on average, even though we've imposed no structure on this function Q. We haven't even imposed that it's differentiable, and we've imposed no other stochastic assumptions on the unobserved shock delta epsilon. So without any of those assumptions, just from this restriction on the size of the shock, we can conclude that demand had to be inelastic on average between most of these periods. And in many periods, we can say much more than that. So like this is a period when we can actually conclude that the elasticity had to be pretty small. Now, this analysis imposes no structure at all on the function Q. That's interesting to see, but it might be that in real applications, we're comfortable assuming a certain degree of smoothness or other regularity in this function. So one way to illustrate the implications of doing that is to assume that the function is a polynomial of known degree, and then to ask what implications follow for the feasible average slopes. So that's what I'll show you on the next slide. So here, I'm showing you for each period what bound we can get on the average slope between that period and the preceding period from assuming that the shock is no larger than 0.07 and that the demand curve is a polynomial of a given degree. So if we assume that the demand curve is a polynomial of degree 1, that's this light gray stuff up here, then we get a uniform bound, of course, because the slope has to be the same in all periods. And the bound is the same as the one we saw before. It's about -0.12, because this takes us back to the case that we were in earlier when we were assuming a linear relationship. But what I think is interesting here is that even if we go all the way up to a polynomial of degree 6, which is a pretty wiggly function over this kind of time scale, we can still get bounds on the average slope that are much tighter than what we got when we put no structure on Q. So even with what I would think of as pretty mild structure on this function Q, that I, as an empirical researcher, might be comfortable imposing, and that's certainly much more general than the linear structure that is sometimes assumed, and that was assumed in the article that we're studying, we can still get bounds that are pretty informative. And so you can see here that a lot of the time we're able to say that the elasticity must have been below 0.3 in absolute value, and in all periods, we can conclude that demand had to be price inelastic on average. So I would argue from this that we're able to get a lot of information about the average elasticity or average slope of demand just by imposing what I would think of as reasonable a priori assumptions on the shocks and reasonable a priori assumptions on the shape of the function itself. Okay, so let me wrap up here. I hope that I've shown you that a priori reasonable bounds on the size of economic shocks can in turn imply a restriction on the slope parameter in a linear economic model or the average slope in a nonlinear economic model. And in application to the world market for food grain, hopefully I've convinced you that this approach can yield informative bounds on parameters of interest to social scientists and of interest for public policy. Thank you.
All right. I assume everyone can hear me. Okay. Thank you, Jesse, for that presentation. At this point, Jesse is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. If you wish to be recognized and ask your question via audio, please indicate that in the Q&A text box. Otherwise, I will just read the text of your question during this Q&A period. And while we're waiting for questions to come in from the audience, I'd like to ask some things. So the first thing I thought of here when I was watching your presentation was that the general idea of allowing slopes and intercepts to vary is pretty similar to what you might expect from a multi-level model, maybe a Bayesian model. You can impose some form of structure on the relationships in the data set to identify those changes. You can model covariates that influence the potential size of those changes. You could certainly estimate a bound on those changes if you wanted to, that would come from the data and from whatever assumptions you imposed on the structure of the multi-level model. And what I'm curious about is how is your technique distinguishable, either better, worse, indifferent, advantages or disadvantages compared to constructing a multi-level model that allows for some form of random slope?
Okay, so great question. So maybe let me break that question into two parts. So one part has to do with allowing for a random slope, and the other part has to do with sort of a Bayesian approach versus the kind of approach that we're taking here. So let me take them in that order. So allowing for some kind of, if by random slope you mean a slope that might be time varying, for example, that is exactly the kind of thing that is implicitly permitted by the analysis that I showed you with the nonlinear function. So that function Q, it's not allowed to change over time, but it is allowed to depend on where we are on the demand curve. And then in the paper we have, I mentioned this very briefly, and I don't have slides on it unfortunately, but I can talk you through it. In the paper we allow for this case here where the epsilon actually enters the Q, and so that implicitly allows for time variation in the Q function. So it allows for basically kind of any structure. And what we show there is that in that case, the bounds you get on the average slope, where you have to now take a little bit of care to define that in a particular way. So that's the average slope at a particular epsilon. And that's something that we detail in the paper, and I don't have the equations here. But in any case, I think a reasonable definition of an average slope there, we get bounds that are exactly the same as this equation here. So that analysis where you allow for a time varying slope is going to get you back to something that looks exactly like this. You're going to be able to say that this is the bound on the slope between any two time periods. So that's what we can say about that. Now, another piece of your question, or another piece of how I take your question, is another direction to go for incorporating a priori information about the sort of plausible size of these shocks would be to take a Bayesian approach and put some kind of prior on that. And I am, speaking just totally for myself, this isn't something we address in the paper, but just speaking totally for myself, I think that's great. And I am totally on board for that. I think our perspective in this paper is that in many situations of interest, we're looking at data from the past. That's almost always true in my experience. And we know something about what happened in that past. So here we're looking at post-World War II market for food, and we know something about what things were happening during that time. And so we might be prepared to say something not just probabilistic about these unobservables, but actually say something concrete about these unobservables, like they weren't bigger than 5% or 10% or whatever. And it might be that if we were looking at a different time period when maybe there was a big war or something like that, then we maybe would be prepared to assume something different. So I think we see this as a reasonable kind of assumption to make in some situations of interest to social scientists. But I think I take the broader point to be, we as social scientists have information about the size of these unobserved shocks that we're sometimes not incorporating in our analysis, and that are potentially informative for the things we want to learn. And so if we were to bring that information in, then we would be able to make more informative statements about the quantities of interest. And I think I see this sort of Bayesian perspective on empirical research is very compatible with that.
When I was asking the question, what I was thinking of was really more oriented toward multi-level modeling, but that's often taught in a Bayesian context. But of course, you can set a flat prior or a very diffuse prior if you don't want to put any information, into a priori information into the model. And what I was mostly trying to figure out is, like, for example, if I'm teaching students, how to build random slope models or models that allow for shocks to the relationship, as you're mentioning. Is there some advantage of taking your approach as opposed to taking I guess you would call it a structural or multi-level approach, where you say, okay, here's there's a function of the slope takes its own function, it takes its distribution, that distribution has some parameters that influence its mean, and then we use the data to inform that. And if this is a supply-demand kind of situation, we might even try to build a simultaneous equations model. If we can just identify one side of that, maybe we don't need to do that. That's what I was. The Bayesian part of it, the prior part of it is important, but I was really thinking more of the structural part of it.
So, I mean, the model, I guess, depends what you have in mind. I guess the model that I showed here is a structural simultaneous equations model. We just only looked at one of the equations.
Right.
And in the paper, we look at the other one and kind of complete the picture. And actually, in this piece of the analysis here, we're actually implicitly using both. We just didn't, I didn't really show that much about where this comes from and what goes on the supply side. So this is a structural model, and it can be derived from, microeconomic primitives if we want to do that. I guess the other part of what you're saying is we might know something about what determines the slope. So for example, we might, in this kind of situation here, we might know something about what this function should look like. Like maybe we know that the slope is a number that's, random depending on time, and it comes from some distribution, or we might know that it's a function of something else like income, or it's a continuous function of time. If we know those things, then I would say, again, just speaking for myself, we should incorporate that information too. And I guess our point is just that in addition to whatever we know about this, there's often something, or not, there's in some important situations, something we can say about this. And by saying something about the plausible magnitude of this epsilon here, or the changes in this epsilon, we can learn things about the unobserved or unknown parts of this function Q. And I think that would be our point. So my expectation would be that if you started here and you said, well, I'm prepared to assume that, say, that there's a coefficient and that coefficient has to evolve linearly in time, then you're going to get much tighter bounds because you've imposed a lot of additional structure. And that's great. If you think that that structure is reasonable for your setting, I would say you should impose it. And our point here is just to say, even if we don't know any of that stuff, we have no idea what this Q looks like, we can still say something about how its slope on average between adjacent periods just by imposing what we might be prepared to impose about these shocks. And I think that's potentially useful because I think there are important situations in which social scientists might have that kind of information available and not be incorporating it into their modeling. I think that's the main point I would stress on that.
I'm glad you brought that up because we have a question from the audience that's definitely on that point. Seth Hill asked, or actually I guess he first said, he was surprised that the degree 6 polynomial did not blow up the bounds. Do you have intuition for why that's the case? Is that something specific to the data, or is that something we would expect to see generally?
Yeah, so I saw that question in the Q&A. So I can offer an intuition for why that's the case. I can't say whether it's going to be true generally, because obviously that's going to be dependent on the realization. But I think intuitively what's going on, so the question, just for context for people who are following along, the question is, it's surprising that, say even with polynomial degree 6, we can still impose such tight bounds. And I think really we were surprised by that too. So we spent a lot of time trying to understand that. And I think the thing to keep in mind is that unlike here, where we're allowing the function to differ arbitrarily between adjacent periods, here, even with degree 6, there's some connection between where the function has to be, say, at this point and where the function is over here. And that, because slopes are so constrained in so many of these periods, that turns out to be enough to limit the leverage that the function can get to wiggle around, because it has to stay inside these bounds everywhere. So yeah, I did find that surprising. I agree with that. I don't know whether that will be true for, every data set, and I'm sure we could construct data where it isn't true. But I thought it was interesting that in this application, which is an important economic application with some policy relevance, that even what I would have thought of as pretty unrestrictive or pretty loose restrictions on the shape of the function still allow us to make such informative statements about average slope. So thank you, Seth.
I was actually had a sort of related question, which is, if you let a demand function get too crazy, you might end up with things like, multiple equilibria or sort of really weirdly shifting patterns. You're not going to get a nice constant elasticity or even an elasticity that's sort of nicely bounded. And I was kind of just wondering, like, what is a can we count on there existing a market equilibrium if the demand function is a 6-degree polynomial? What does it mean to talk about elasticity when the demand function is that free?
Yeah, so in this case, I didn't go into this detail, but for these calculations where we're allowing for polynomial, so here we only show the negative slopes that are permitted given the bound, just like consistent with our linear model. So we're assuming demand slopes down. And in this analysis here, we're imposing that this polynomial has to have a non-positive slope everywhere.
Yeah.
So that is, it has to slope down. And given that it slopes down, unless it's literally flat, you won't have multiple equilibria. So if you have a strictly downward sloping demand curve everywhere, you won't have multiple equilibria. You'll always have a well-defined competitive equilibrium. And that is also, and I should have said this in response to Seth's question, that is also some of the reason why we're able to have such an informative conclusion, because the function is not allowed to, go like this.
Yep.
It can't jump up and then go back down because it has to always be downward sloping. One thing that I'll say is that, for the parts of the analysis where we're analyzing the demand side of the model, we're not really imposing perfect competition or any notion of equilibrium, because we're just saying that whatever price quantity pair we observe has to be on the demand curve. No matter what supply conditions give rise to that, we must be on the demand curve. And that by itself is enough to get the results that I showed you. So we aren't really, other than saying that there is a curve, there is a demand curve at any point in time, and we have to be on it. And then in the first part of the analysis, of course, we're imposing that curve is linear, and then later we're relaxing that. But other than assuming the existence and then some structure for that demand curve, we're not imposing anything about the way that the market operates until we then impose a supply condition for the other part of the analysis that I showed you.
Well, I don't see any other questions from the audience, so I'm going to thank Jesse for being our presenter this week. His presentation will be posted to our website shortly after this broadcast if you'd like to share the presentation with a colleague or watch it again later. I also want to invite you to join us next week. That'd be Friday, October 30th at noon Eastern, when we will host a talk by Lu-Wei Ying of Washington University in St. Louis. Please see our website, www.methods-colloquium.com, to get more information about this talk. Jesse, I really enjoyed this. Thank you very much for being here today.
Thank you so much, Justin. This was a lot of fun. I really appreciate your questions and Seth's question and the chance to talk to your audience today. Thank you very much.
Hope to see you next week.
Have a good one.